Welcome back to The Explainer. Today, we are diving straight into the absolute bedrock of the physical sciences. Physics is essentially the system we use to map reality. But before we can start charting the universe, we really need to master the basic building blocks. Our goal today is to identify those core concepts and highlight the really important definitions that are going to serve as our fundamental toolkit going forward.
So here is our roadmap for today. We are going to look at 1. Scalars, vectors, and U. 2. Navigating coordinate systems. 3. The power of vector components. 4. Adding vectors together. And finally, 5. Master problem solving. Let's get right into it.
Section 1, Scalars, Vectors, and U.
Okay, let's start with the absolute simplest definition, a scalar. What is it? Well, a scalar is a physical quantity that's completely described by its magnitude, or its size, alone. It's simply an amount, just a number. When you step on a scale to measure your mass, check the time on your watch, or measure the length of a piece of wood, you are dealing with scalars. There's no direction involved here, just a raw number and a unit.
A vector, on the other hand, is a physical quantity that requires both magnitude and a specific direction to be completely described. This is where things get a bit more dynamic. Think about it like this. If I tell you to drive 50 miles per hour, that's a scalar. But if I tell you to drive 50 miles per hour straight north, boom, that's a vector. Velocity, acceleration, displacement, these are all core concepts that absolutely require this directional piece to make any sense.
So the core difference really just boils down to magnitude versus magnitude plus direction. When we represent vectors visually in physics, we draw them as arrows. The length gives us the magnitude, meaning the larger the quantity, the longer the arrow. And the way the tip of the arrow faces, that dictates the direction. It's a remarkably simple, yet super powerful visual tool.
Moving right along to Section 2, Navigating Coordinate Systems.
Now that we have our vectors, they need an arena to live and interact in, right? Our most familiar arena is the Cartesian or rectangular coordinate system. This is your standard grid map. We plot points using an x-axis for horizontal movement and a y-axis for vertical movement. It lets us precisely locate specific positions, like point P at 5, 3, or point Q at -3, 4, literally just by counting the units along these axes.
But there's actually an alternative way to map space, and that's the polar coordinate system. Instead of navigating a grid of horizontal and vertical streets, this system locates a point using a direct line distance, which we call r, from the origin, combined with an angle, theta, measured from a reference line. That reference line is usually just the positive x-axis. It's kind of like telling someone, hey, walk exactly 100 meters at a 45-degree angle. Both of these systems are absolutely essential for mapping vectors. Which brings us to Section 3, the power of vector components. Here's where we highlight a really crucial definition, vector components. These are the projections of a vector parallel to the x-axis or y-axis. By projecting a diagonal vector down onto our axes, it forms a right triangle with the original vector acting as the hypotenuse. We can then use basic trigonometry to calculate exactly how much of a vector pushes horizontally and how much pushes vertically. To really see this in practice, imagine a superhero flying downward off a tall building, moving, say, 100 meters at a 30-degree angle. By applying these component principles, we can slice his flight path into an x component for the horizontal distance he moved away from the building and a y component for his vertical drop. This basically turns one tricky diagonal movement into two perfectly solvable, bite-sized mathematical pieces. All right, Section 4, Adding Vectors Together. When you're adding vectors, you can't just mash raw numbers together if they point in different directions. You actually have to follow geometric rules. Using the triangle method, you draw the first vector and then connect the tail of the second vector to the head of the first. Or you can use the parallelogram method, where both tails start at the exact same origin point. Oh, and keep the associative rule in mind. No matter what order you add these vectors in, your final destination is going to be exactly the same. Take a hiker going on a 2-day trek, for example. Day 1 is vector A, heading southeast. Day 2 is vector B, heading northeast. By connecting the tail of vector B to the head of vector A, we create a triangle. That new arrow drawn straight from the starting base camp to the final destination, that's our resultant vector. It's our total displacement, completely bypassing the zigzag path they actually walked.
And finally, Section 5, Master Problem Solving.
The source material gives us this fantastic, comprehensive 8-step guide to physics problem solving. It moves systematically from just reading the problem all the way to checking the answer. And this structure is vital because physics isn't just about plugging numbers into a calculator hoping for the best. It's about methodically translating a messy real-world scenario into a clean, solvable mathematical framework.
Actually, we can distill those 8 steps into 4 core milestones. Visualize by drawing a diagram. Identify by labeling your quantities and principles. Solve symbolically by choosing the right equations. And finally, calculate by substituting your known values to get the answer. Doing this turns a potentially overwhelming physics problem into a highly predictable, step-by-step process.
Let's apply this strategy to something mundane, like a shopping trip. A shopper drives to a store, we'll call that vector A, and then to a restaurant, vector B. After drawing our map, we recognize we need to solve for the resultant displacement, vector R. By breaking A and B into those components we talked about, adding them up, and applying some quick trigonometry, we find the exact straight-line distance and direction from home to the restaurant. It works flawlessly every single time. We've covered a ton of ground today. We've identified the core concepts of scalars and vectors, and we've highlighted the crucial definitions that let us map and measure reality. You've got the mathematical tools, the coordinate systems, and a rock-solid problem-solving strategy in your back pocket. So here's my final question for you. Now that you have the tools to map the universe, what are you going to put in it? Keep exploring, keep questioning, and I'll catch you in the next explainer.